Share the screen and that's back.
Waiting. Why is it waiting?
This is live.
So now we go back to it. And the situation.
Yeah.
All right. Sorry for the little delay over here. We were trying to do this for the live audience. We had to change computers in the middle. So right now we have one computer which is doing the video and audio. Come closer enough, I can use your mic. We have another computer for the live streaming. So hopefully it's all working. Now, let me introduce today's speaker. Deepashankar Chattopadhyay is a final year PhD scholar in TIFR in the Department of Theoretical Physics, where his research is about neutrinos. He can tell you more details about that. But he is also a very fascinating science communicator who can make things simple, especially things as complicated as quantum mechanics. Which I think is something which all of us struggle to comprehend. And to take you into this, what he calls the weird and wonderful world of quantum mechanics, which I think is a mind-boggling world of quantum mechanics. You can introduce where you're from and all that.
Well,
IIT Bombay.
Yeah, I did my master's in IIT Bombay,
and
then I'm
and then in TIFR. Okay. He likes all sorts of things. Excellent photographer.
Thank you.
Yes, so we will share screen and get started with
it. Yeah, absolutely.
Okay. So we are in this weird superposition state of two computers.
Yes, and hopefully they don't collapse.
Right. Let's hope there's no wave function collapse over here. So let me start the share screen with this. Share. Okay.
Okay.
And I'll do one thing. I'm going to hide this. Put it out of the way so it won't bug you. Okay, and this one also I will hide floating meeting controls. Okay,
great.
So we are all set, and you need to tell me, or you can advance slides yourself, whatever you want.
Sure. So what I'll do basically is you'll see me moving a lot in this direction over the talk. But anyway, let me start. Right, I'm Dibbo, and today we are going to go to the weird and the wonderful world of quantum mechanics. Right. I mean, I don't know if you have seen the poster. I certainly had to. And let me go through just the key lines of that. What are we asking? We are asking that how do the fundamental building blocks of this world behave? What we see right now with us is not exactly what is the inherent nature of what we are made of. What do I mean? I mean that we're made of particles. We're made of subatomic stuff. How do they behave? Do they behave the way we expect them to? How far will our intuition take us until it starts becoming mind-bogglingly weird? Because believe me, you will feel, unless you have had like a physics experience, you will probably feel at some point in the talk that maybe I'm not right in the head, but well, hopefully I am. And finally, what do? We embark on a journey to explore the weird and the wonderful world of quantum mechanics, where our classical intuition starts failing with each experimental observation and contradicting behaviors emerge. So all that is good, except I have told you nothing about what we are going to talk about so far. I have just told you one key phrase, that quantum mechanics. So Marie Curie once said that be less curious about people and more curious about ideas. I think it's, well, not just for this talk, but it's a nice sentiment. But in general, we're going to go to the deeper fundamental nature of the universe. And you might think, why? And of course, there are many reasons why. You don't really need a reason to probe the fundamental nature of the universe. But then there has also been this Nobel Prize. So the fundamental nature is currently also trending, per se. In 2022, you can see Alan Aspect, John F. Clauser, and Anton Zeilinger. The three of them, they got the Nobel Prize because they probed a deep fundamental implication of quantum mechanics. And they proved it right. There was something that the theorists had predict, and there was the first experimental confirmation over many years. This did not happen in 1 year, 2 years. It happened over tens of years, decades, that finally they were able to prove that indeed the quantum mechanical world is as weird as people expected it to be, or rather people expected it would not be. Because, so that part I'll come to, of course, later. But basically, to even talk about what they did, first we need to go to the very basics. First, we need to start with the nature of light itself, and by asking that what is light? Now, what is light? Newton said that light is made up of small discrete particles called corpuscles, little particles, it means, and they travel in a straight line. So think of the Newtonian era. Here's this guy saying that, okay, light is made up of very tiny particles. But of course, science progresses, and then comes the Huygens-Fresnel's principle. So what is light? They say that on a light is basically a wave. And on a wave front, every point itself is creating further spherical waves. So it's like light is going like this. And then from every point of that, again, light is going like, it's like ripples in the pond. You can think of this. And this new wave front, that from this one wave front to the next wave front, is just caused by summation of each of these spherical wavelets, like here. So each of these waves individually are creating the next set of this final behavior. So then now we are talking about light is a wave. And this is something that we can closely associate to, because we know that as an electromagnetic wave, the nature of light is seen in everyday phenomena. You can see reflection. When you see anything like looking at a pond, a lake, or maybe the Arabian Sea on a clear day, but probably not because it's so polluted here, that you would see this image. Well, not this image because this mountain is in US, but some image. On the other hand, light also refracts, and you can see refraction. And right now it's the Mumbai monsoon, so it's like really great observation. Just go back home, find a water droplet, and what you will observe is this light, because of the properties of the light, you will see an inverted image of whatever is in front of you. So light is an electromagnetic wave. Sorry, yeah. Or is it? Because you know, the light is an electromagnetic wave, and if that was that, then the talk would end here. So is it? So comes the photoelectric effect. So this is the point, like 120 years ago, roughly, where scientists know that light is an electromagnetic wave. Some scientists even think that we basically know, we basically understand all the things there is to understand about the universe. But there are some small discrepancies arising here and there. For example, take this, the photoelectric effect. So what is the photoelectric effect? There's a photo, there's electric. So it's something to do with light and electrons. In fact, what it is that if you shine some light onto a material, you expect some of those electrons of the material to escape. Except to escape anything really, you need a certain amount of energy. Where do you get that energy? You shine light. That's how you get the energy. So the light falls. This is what scientists understand so far. Light falls. It excites the electrons get some energy, and some of these electrons are actually able to escape the material. And once the electron is ejected, you can actually observe that electron from your detector. Great. But then, what does the wave nature of light suggest? The wave nature of light suggests that if light is really a continuous wave, suppose you have a light, and this light is giving you some energy. However, it just may be that the energy needed to escape is larger. So what do? You would expect that you would shine the light for a longer time so that the energy builds up, builds up, builds up, and eventually it escapes. Or maybe you would expect that the more intense the light is, because of the more likely that the electron will escape, even when light itself is having low frequency. Low frequency means what? Light ka energy comes. However, what did we observe? We observed that below a certain frequency, below a certain threshold, no matter how much light you shine on this material, for how long, with whatever intensity, you simply do not get more energetic electrons. Because what happens is when the electrons are escaping the material, they are taking away some of this excess energy with them. Suppose, I'll give you an example, right? Suppose you want to have, I don't know, like 1 cup of coffee, but except that is the amount of coffee you need to escape your drowsiness. You just woke up, right? Except that you suddenly end up having 2 cups of coffee, or maybe espresso with 2 shots. You will feel that, and others around you will also feel that. Except what is happening here is no matter how much light you are shining, the electrons are never any more energetic. They have some maximum energy, and that's it. Now you switch on more lights, nothing happens. Only thing that happens is you get more electrons, but never more energy of an individual electron. Comes Albert Einstein, of course, right? Albert Einstein explains that, look, light may be a wave, but in this particular instance, you have to explain it in this way, that light consists of quanta, packets of fixed energies corresponding to the frequencies of the light. And what happens is when you shine light on a material, these electrons, they don't feel all of the light. They feel this one quanta. That is what they have. Now this one quanta, however much energy it has, some of it is used in escaping the material, and the rest of it is used in electrons being too fast. So comes the first time properly the concept of photon. So this is photon called one light quantum, and this photon must have at least some energy, because nato the electron will not get enough energy to even escape. And which is why there is a frequency cutoff. Below a certain frequency, the photon simply does not have enough energy to supply it to the electron so that the electron can escape. So comes photoelectric effect. So then what is light? Right. So is it a wave or is it particle? Because now we just heard Albert Einstein said on one hand, there's a photon, which is a quanta of energy, and this is how you explain photoelectric effect. On the other hand, there's the wave nature of light, which is seen every day. Every time you see a reflection, you see a diffraction. So I would ask the audience that how many of you think that light is a wave? Just shout or something. Okay, great. Great. And how many of you think that light is a particle? Okay, I see some of you raised hands on both the cases. So yeah, not a really surprise, but anyway. And I'll give you the answer, but just like any good show, the answer will come in 2 more minutes. So is it a particle? So what do we predict? So this is a very famous experiment. Ah, great. Who was it? Ah, great. Okay, so this is the double slit experiment. Now, if light was a particle, you would expect, because there are double slit, that you would expect 2 signals on your screen. 2 signals, that's it, right? I mean, think of this as shooting water pellet gun during Holi. You expect that if there is an opening, that guy will get drenched. On the other hand, if light is a wave, then you expect more convoluted, more complex cases. Because then what would happen is, as we talked about this, that each of these openings would create as sources of waves. This is the Huygens-Fresnel's principle. And then you would get some weird different structure. And we end up asking that what do we observe? So you observe this. This is the interference pattern coming from double slit experiment. And you clearly see that it's not just two lines corresponding to two slits. You have in fact seen this, a different version of this, when it rains. If you look at the pond and if you look at the ripples of the rain, each ripple will create an outgoing wave, circular in nature. And each of these waves, they interfere with each other. They sometimes increase the wave. They sometimes decrease it. So this is called constructive and destructive interference. Although like scientists try to sound a bit more professional, but basically that is what is happening is this. The interference of the waves coming from these two slits is creating ripples where you finally get this wave intensity pattern. Sometimes the waves cancel each other out, right? One wave is going like this, the other is going like this, they will cancel each other out. Both waves is going like this, you will get more signal. So this is the interference. And in fact, what is like? It is both. Yes.
Depends on whether the open surface of the
Correct. Correct. So in fact, great point. And this is something I spoiler de diya, yeah. Huh?
Somebody on YouTube said it's a vehicle.
Ah, that's a nice name. Unfortunately, we did not think of this, but yeah, great. Okay. So you gave me a spoiler, but okay. Let us continue. Now we ask, what is an electron? So who among us believe that electron is a particle? Great. And now at this point, I know that you know my game. You are thinking, he's asking that if it's a particle, and right now he will of course try to prove that it's not. I mean, that's the general theme. Or is it? And in fact, that is exactly what you saw. The electrons through the double slit also create the same interference patterns that we earlier saw. And in fact, this experiment is very special because this experiment proves something very intriguing. It's not just that, let's suppose you have hundreds of particles going together and then some of them are interfering with other particles and finally giving you this picture. No, it's not a statistical property. It is the property of each of these particles that they are both a particle and wave. As this guy said, that you actually end up, this answer depends on whether it's being observed or not. So when not observing electrons, what do? You put one electron through the apparatus at one time, and you let the signal build up, the signal accumulates. Each of these electrons, in fact, pass through both the slits at the same time and interferes with itself because of the wave nature of this particle. And this is how they proved, by actually passing single electrons through the double slit and finally observing the interference pattern in 1989. So electrons through double slit, the same exact thing happening, and we get the interference. So the electron is also a wave. And in fact, this is called the wave particle duality, or as someone in YouTube said, wavicle, which is a catchy name, but it may not catch up in the scientific community as much. We are very picky about not changing names because then we have to go through all the textbooks again. So all particles have wave nature, and this manifestation of wave nature can happen for any subatomic particle. But when you're talking about the wave nature, you of course try to talk about wavelength. So does everyone know what a wavelength is? Can anyone answer for me? Okay, so you have, let me go to someone else, I'll come back to you. Bolo.
Distance from like one point of the way of a single wave to the other point to the same point on another way. The distance.
Okay, I think exactly what you mean to say is some feature of the wave to the same feature again. Right, great. So for example, peak to peak or valley to valley, or for example, midpoint to midpoint, as you say. So this is one wavelength. And this crazy looking guy, Louis de Broglie, says that, look, I know how to calculate the wavelength of a particle. It's just the wavelength lambda equals to h by p. What h? What p? So p is obviously the momentum, but p is actually mass into velocity. So now you know, if you decrease the mass of something, what happens to the wavelength? Great. And if you increase the mass, then the wavelength, correct. This is something we'll come back to slightly later. But first, let us ask, what is h? So who knows what is h? Okay, go ahead. Great. And okay, so in my other version of slides, I would have asked the value, but the animations are gone. So this is Planck's constant. Now this is in SI units, joules second, and then 6.6 into 10 power minus 34. Do you know how small that number is? Great, but let me show you anyway. So there are this many zeros on the number, after which the first non-zero comes in. So this is how small the number is. Okay, so some number is small. With respect to what? I can say I am small with respect to the Empire State Building, right? So we ask, where exactly does the quantum nature of things show up? They show up at the level of electrons, at the level of protons, at the subatomic level. Now, it is worthwhile to point out that the ratio between the mass of an electron versus this 1 kg weight is almost similar to the ratio between this 1 kg weight and the mass of the sun itself. So if you just started gathering electrons, and you cannot, but hypothetically, if you did, the number of electrons you would need to have 1 kg of electron and the number of 1 kg weights that you will need to make an object as massive as the sun are similar. So that is how tiny the scales of nature is where quantum mechanics actually shows up. And that is exactly why, thankfully, as I'm talking, I'm not suddenly transforming into a wave and just going out of the door. But if you ask me very difficult questions, I just might. So how do we know then, it's a wave, it's a particle. Where is this particle? How do we know that? Can we pinpoint where it is? Does anyone know the answer? This is fairly, okay. Close, yes. Actually very interesting, yes. Okay. Yes, I mean, see, when you say everywhere, so maybe this is a good point actually, because you gave that answer, to point out that while in principle a particle can be everywhere, the wavelength of the particle, the lambda that we just calculated, is roughly where it will be seen most of the time. But actually, what I'm asking is, maybe I should ask in a different manner, is can you actually precisely pinpoint the position of the particle? Exactly. And as this everywhere answer suggests, that not really. So this is the uncertainty principle, that nature inherently is fuzzy. We cannot measure the location and momentum of any particle precisely at the same time. And this is, Werner Heisenberg said this, wrote down this equation, and immediately became famous. So there's the uncertainty principle which says that del x, which is the error in measuring the location, into delta p, which is the error in measuring the momentum, is always greater than some value, which is h, the Planck's constant, by 4 pi. Interestingly, this is a theoretical limit. It's not that if you someday manage to somehow build some better experimental apparatus, you will finally break this. No. Nature inherently is fuzzy, which is why I also kept my title as fuzzy. I hope you have noticed. But what happens is somewhat like this. It's not exactly this, but I want to give you a mental picture. Think of playing carom blindfolded. Or maybe the room simply doesn't have any light. You forgot to pay the electricity bill. So there are coins in the board. And you want to know what the coins are. But of course, you cannot see them. The only way to see would be to actually use the striker and then try to pinpoint by striking the coin with the striker that where the coin is. Now, if you exactly want to know where the coin is, you strike very hard. Sharp sound comes in, and you know, okay, the coin was there. Great. Except that because you strike it so hard, now that you have imparted a certain velocity to this coin, and you don't know that what is the velocity of the coin, which direction it went, you don't know that. Whereas if you strike very softly, you will not be able to exactly pinpoint from which part of the board the sound is coming from. On the other hand, you would not also give the coin a large velocity. Now, this analogy may make you think that, okay, then the particle is surely somewhere. But maybe we don't know where it is. We cannot see. The light is not turned on in our room, in our quantum room. But no, these two can be disproven. So it can be exactly proven that the particle is actually everywhere. It's not, unlike this example that I gave, it's not that the coin is at a particular position. How do you prove this? You prove this, as already pointed out, by not observing the particle and putting it into a double slit. See, if we did not know where the particle was before observing, but nature somehow knew, there's a hidden information, right? That we cannot access that information, but the information is there. Then this particle would have gone through, there are two slits, one of them. But it did not. We sent single electrons at one time for a long time, because finally we also need a lot of signal. नहीं तो कुछ दिखाई नहीं देगा. And then we saw that interference is still happening. Even a single particle is going through both the slits. So indeed, the particle is everywhere. So now that we kind of understand that, okay, quantum mechanics is sort of weird. It can be a particle, it can be a wave, it is both, and that actually shows up in experiments. Now let's play a game. And this is where I'll need your involvement, definitely. But this game is that of Bell's inequality. And this is a complicated game, and I will not make you play till the end of it, because then, see, there are certain processes that you must follow to get to know a subject. Right now is a primer to quantum mechanics. Now, if I said, okay, look, A, B, C, D, Shakespeare, then no one would read English again. And this is a bit like that. But let us go through the ABCD. In fact, let us go through A and B, Alice and Bob. So can we get a Alice out of this crowd? In fact, no woman participant yet. Someone, anyone? It's just I will not ask you physics quiz, pakka, promise. Okay, great. Huh. And can we get a Bob? Okay. Huh? Huh. Come to the stage, please. Okay. Tell me what Schrodinger equation means. No, just kidding. Huh. Oh, yes, please.
The Schrodinger equation is the wave function of how the particle would behave if it was a wave. So it's like it tells the probability of where it can be the most and where it's not.
Which grade are you in? Okay. Great. This is great. In grade 9, I had zero clue. I would not even be able to probably pronounce Schrodinger properly. But well, I should be careful of you. But anyway, so let us now just choose. It's simple, right? The game is simple right now. You choose +1 or -1. In fact, both of you must run 2 experiments. So you run 2 experiments and you run 2 experiments. And think of either +1 or -1, any combination. Plus, 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 minus, minus, whatever. So first you give me 2 numbers. 1, 1. You give me? -1, 1. Great. So you're of course Alice for this experiment. And you have given me 1, 1. So you see, and this is the quantity we are measuring. Now A1 and A2 both are 1. Remember this. And you gave me?
1 minus 1.
Correct. So B1 plus B2 is 0. But B1 minus B2 is 2.
Yeah.
Correct. So the final number becomes 1 into 2, 2. Great. Let's try one more time. Give me some other set of numbers.
-1, -1.
-1, -1.
-1, 1.
-1, 1. Okay. So again, on both A1 and A1, and you have given me -1 and 1. So this again goes to 0, and this one becomes -2. But into -1 is again 2. Do you see something? I mean, yes, you, huh?
The same pattern.
Yeah, you could get less than 2. Unfortunately, you didn't come up with an example, and how many times would I ask? Then you would eventually get annoyed. You could be less than 2, but you could never cross more than 2. So this is, in fact, something that can be shown. I do not show all the rows because then the audience will fall asleep. But you can never cross 2. It is impossible to make this value greater than 2. Or, judging by the same thing going as the same before, is it? So how to win a Nobel Prize? All you need to do is show that this value can become greater than 2. Easier said than done, clearly, because otherwise no Nobel Prize. But in fact, this particular measure can become as large as 2√2. And this is the game of Bell's inequality, where you can prove this concept called entanglement. Now, I do not have the capability to explain entanglement in simple words. I myself need a lot of time to even try to understand what it is. But just let me tell you how the quantum world can be quite unintuitive. So the entanglement is called spooky action at a distance. But of course, what is entanglement? Entangled particles remain connected even when separated by vast distances. Yes?
But they somehow disconnect when you observe them.
Correct. But they disconnect in a very specific way. Does anyone know? Okay, of course you know. Huh? Go ahead. Go ahead. It's great. Oh, I see. Ah, right. Huh, huh, huh. So, audience cannot hear me?
Audience cannot hear what's happening.
here, so please repeat it for the sake of the online.
Okay, okay. So we're talking about entanglement, and we talked about how entangled particles remain connected. So a bright young fellow from the audience points out that entangled particles remain connected, but they disconnect when observed. So I asked him back that how? Bolo.
They connect by feeling in the same way, and when you observe them, it's not. They don't.
Great. In fact, so okay, maybe a round of applause for him, right? Yeah. In fact, so I will not go to the concept of spin, but let me go to the concept of polarization. So it is just light, because you know the theme seems to be light and quantum mechanics. Light is a wave, and in fact, it can vibrate, you can think of, in a particular direction. As it travels, it can travel like this, like a wave, or it can travel like this. Sorry? Ah, yeah, well, yes, but hopefully it doesn't bite you. But yeah, you read enough physics, you start to feel like it is biting you. Yeah, but huh, huh. So what's happening is when you create light under certain processes, you have their polarization connected, but you don't know of these two photons what is their individual polarization. You only know the sum of it. What happens is when you observe, maybe you get this light is going like this and this light is going like this or something. However, no matter how far away these two photons are, during observation, as soon as you observe one of the photons to have a certain polarization, the other particle's polarization also gets fixed. Even if the first experiment is happening in Earth and the second one, like in Mars or something, we haven't done an experiment in Mars yet, but we have done quite a few meters away, so long distances away. Even then, you see this, that these, yes. Yeah, it's also true with random polarizations, yes. In fact, here, for example, the polarization that is shown is actually unpolarized light. So it's neither vertical nor horizontal. It's just that we show the projection. Actually, it's randomly polarized, unpolarized, in fact, and then you finally can create polarized light. However, that's a story for another day. But what happens is that this is the crux of it. Two states which are very far away from each other and have absolutely no way to talk to each other. Even then, if you measure one of them, the other one's properties get fixed on that instant. And this is something that is so mind-boggling that Einstein himself said that, look, this is just weird. This cannot be. So this is actually, I think, the New York Times snapshot from 1935 or something. The Einstein attacks quantum theory, believes a whole description of the physical reality. Also the irony, right? Because Einstein is the one who first comes up with this concept that, look, photons are traveling as packets of energy, quanta. And from that, these other young scientists, they build up this whole quantum mechanics. And then Einstein's like, no, there must be something wrong. Now, of course, he had quite a good track record. When he said there must be something wrong, often there was. Except the Nobel Prize you receive is for experimentally proving that indeed there is nothing wrong. This is exactly how nature is. This is called violation of local realism. Heavy words. Yes.
So when the light is created, it has certain polarization. Does the polarization of light change over?
That too can happen. So audience, member from audience asked that when the light was created, does it have a certain polarization and can it change?
Does it feel natural without any interference from humans?
Humans? No. Do you mean naturally or no? Because we may or may not do anything to change it. See, here is the thing. Okay, let me give you a more accurate description. Polarization of light can change as they travel through, for example, a medium. However, we don't need to actively do it. We can also do stuff to it and change it, but that too is naturally changing. Yeah.
So follow-up question, there are two entangled light particles
Yes.
different directions
Hmm.
and two different mediums.
Hmm.
In spite of their polarization being affected by the different mediums, would the polarization still, the total polarization still be same when measured? Because they are entangled?
No, so they don't remain entangled if you disturb them too much. As this was pointed out, that at the point of observation, entanglement breaks. Observation is not that I got to know something. Observation is just disturbing the system. So if you disturb the system, you can probably get away with a certain amount of disturbance, very little, but because of course there is no ideal clean system in the world. But entanglement breaks if you change it too much. So it's not that as it propagates through the medium, the other one will feel it that way. The moment it feels the first hit is the moment that they're like, okay, fine, chalo, bye bye. So it's a bit complicated to, but yeah, because for example, this may make it seem like there is, you have two lights. Maybe you observe the polarization of one of them on Earth, and maybe you create them in from the middle of Mars and Earth. Right, here is Mars, here is Earth. Okay, Earth is slightly bigger, and you observe the polarization of light in Earth, and that would change something on Mars. You might think that this is faster than light communication because it's instantaneous, but this too can be shown that it's not. In fact, what's happening is just this. Realism is the concept that physical objects have definite properties that exist independently of measurement. This is not true, which is why you end up seeing this. Basically saying that until you measure the property could be a plethora of things. It could be this, it could be that, it could be maybe even something in the middle. But it's not predefined that what we will see. So now that we have sort of really gone to the deep end, let us come back out slightly, because I don't want to end my talk by saying, okay, here is something that you will not understand, and go home. I want to end with something that you can relate to, but which is equally weird. Which is, okay, mistake, but anyway, no problem. So suppose I'm coming from TIFR to Prithvi Theatre, and I need to reach in time because the talk is starting at 11. Now, just for the sake of honesty, I'll point out that we took a vehicle, but suppose we did not. So what would be the mode of transport? You go to Churchgate, you take a train, you don't point out the mistake right now. You end up at Andheri, and finally you are taking an auto to Prithvi Theatre. Ville parle utarna tha, so kya hoga? Auto mil nahi raha. So what will happen, in fact, is the probability of reaching Prithvi Theatre in time is the probability of me reaching to Churchgate in time for that train. Then the trains running in this monsoon on time, And finally, from Andheri, I must take an auto. Well, we all know out of the three, Andheri se auto milna mushkil hai. But the final probability is P1 into P2 into P3. The chance that you are successful to reach in time is chance of success at each step. In fact, here itself you see that there are multiple other routes that you can also take. Maybe you can take a bus. If you're crazy enough, maybe, if you're crazy enough, maybe you can swim to Prithvi Theatre. I don't know. But there are multiple ways to reach. And all these probabilities of each of these successive steps, first you multiply each of these paths, then you add. And then you finally ask that how many times out of how many times am I reaching Prithvi Theatre in time? We all understand this concept somewhat in day-to-day lives even. We don't calculate it like this because we don't get paid to do that. But we understand this concept. We are going to the office, we have to take a metro. We understand this concept. And here is where I will point out that, in fact, if this is the same for the quantum mechanical world or not. So this is one such example. Suppose you have two states and going by the same thing of choosing +1 or -1 because just easy to understand, right? They're opposite to each other. So this is +1, this is -1. You start at time 0 and here is finally T2. Here is where your particle was, point A. And the particle could be either in the +1 or the -1 state a time T2 later. Fine. Clearly, if the particle can access both states, there is a probability associated with it. Maybe 70% of the time, if you start from +1, you reach here to B. 30% of the time, you reach D. However, now let us observe, let us disturb the system. We now put an observation at T1. And then we ask, what's happening now? Now, obviously, while this was 30-70 here, this would be something else, more likely than not. Maybe right now you start with 100% in +1. Here you get 90% at X and 10% at Y. And then again, something more. Classically, what would you expect? You would expect that this path and this path plus this path and this path would finally take you to B. So you multiply these probabilities, right? This is just TIFR to Churchgate to Prithvi. And this is TIFR to CST to Prithvi. You expect, if you add them, sorry, did I say raised hand? No. If you add them, you just get the final probability of TIFR to Prithvi. And we indeed do classically. But in quantum mechanics, we observe that they are not the same. They are, in fact, different from each other depending on whether you have the intermediate observation or not. Intermediate observations disturb the quantum system. In fact, without an intermediate observation, you can calculate the probability from the wave function formalism. Great. And with an intermediate observation too, and you can show even theoretically they are different and experimentally too. This is also perhaps the point where I do a bit of bragging and point out that this diagram is from a paper of my own. Yeah, fine. But essentially, what's happening is that we are probing the quantum nature of things in many different ways. For example, earlier in Bell's inequality, you saw that particles are separated in space. Now you are seeing propagation of particles in time. What I work on, neutrino physics, Neutrinos are very, very, very tiny subatomic particles. In fact, they are so elusive that neutrinos, like probably I really forgot the number, but I think it's about 100 billion neutrinos passing through your thumb every second, coming from the sun, and none of them hit your thumb. If you are lucky in your lifetime, one neutrino would hit you. And even then, we still do experiment with these particles because that's how crazy we are. Now, what happens when you study weird stuff like quantum mechanics? But here's the interesting thing: these formalism, right now it's for two states, right? +1 or -1. You can also expand this, modify the definitions themselves to look for effects of quantum mechanics when there are more than two possible options. For example, when there are 3, 4, 5 different paths available, even then you can still test for quantum mechanics. Yeah. Should be. Okay. Speaking, can you hear me? Yeah, just 1 second. Keep going. Great. And in fact, I would give you one last example to sort of, it is not an analogy of any sort, but think of it like this. Suppose you are walking from Metro Inox to Marine Drive, and you have 3 different paths which you can take to reach Marine Drive. Whether someone observes you or not does not change your final probability of reaching Marine Drive. However, if you are walking with your girlfriend, and if you did not know where your family members are in Mumbai at that time, depending on observation, that may severely affect your chances of reaching Marine Drive. So, quantum mechanics is a bit like that. It's sneaky. So, even our classical intuitions about the typical intuitions or probabilities fail at the subatomic level. And in fact, this is the quantum nature of things. That the smallest scale, nature is weird, nature is fuzzy. And yet, a few equations that we showed can explain so many different things because we understand quantum mechanics. We understand the experimental observations. We can explain them. And we have been doing that for almost past 90 years, 100 years. So Richard Feynman once said that I think I can safely say that nobody understands quantum mechanics. And in fact, this would go in 3 steps. Today, hopefully, I have been able to prove or show that quantum mechanics is weird. If you study physics, in a few years, in roughly 1-2 years of studying quantum mechanics, you would start to feel like you understand quantum mechanics. I would implore you to go on. In 5 more years, you will again realize you don't. And with that, we are kind of at the end, but essentially using this as the first step, we can go on. We can go on to even more complicated but extremely nice, very fascinating concepts which can explain even how the sun shines. Why does it give out light? How does nuclear fusion work? We can explain flame test exactly that to your nearest chemistry lab, not just ratta, not just cramming. You will know exactly which kind of light you would expect to observe if you understand quantum mechanics. You would know how lasers themselves work. And this is Donna Strickland. She also got a Nobel Prize. You would understand how solar cells work because, and let me tell you, really important things to understand, really important things to build upon, improve further, because there are real issues that solar cells can solve. Climate change, for example, or if you are maybe not as interested in solving climate change, how about going to space? Even our smartphones, they don't use quantum mechanics directly, but the transistors and the CCDs, they are built upon quantum mechanical principles. We are currently building quantum computers at TIFR, at IBM, at many different places. So this is the nature of quantum mechanics. Not only is it fuzzy, not only is it weird, it's also everywhere. Everything that you see at the heart of it is quantum mechanical. You don't see that, sure, because I am not suddenly becoming fuzzy, probably get your eyes checked. I am not suddenly becoming a wave. But every particle that I'm built with are. Even at TIFR, particle physics, astrophysics, chemistry, biology, condensed matter, nuclear, atomic, everything that you take, we go through this every single day. And with that, I'll end by focusing on what did we learn today. We learned about wave-particle duality, that particles and waves are not really so distinct, they can be each other. We learned that quantum mechanics shows up at the smallest scales of nature, and you can actually calculate the wavelength of any object. We learned about the uncertainty principle, that nature inherently is fuzzy. We learned that particles can be connected in weird manners across space. We learned that probabilities simply do not add up because of observation. And we learned a bit more about how fundamental nature of things are, and a bit more about what they are not. And okay, even things you use, even next generation technology, everything uses quantum mechanics. So I'll end with saying this. Now you know and don't know about quantum mechanics. Thank you.
Okay, thank you, Joe. Can you just ask the online audience to type in their questions?
Huh. Okay. To the online audience, please type in any questions that you may have. We'll just take them and end the YouTube session first. Yeah.
So there are a few questions. Maybe some of these are probably a bit technical, but you may want to answer this. What is the difference between Schrödinger's equation and Dirac equation?
Ah, interesting. Good, good. So we are being asked what's the difference between Schrödinger's equation and Dirac's equation. Great question. Well, first of all, you encounter Schrödinger equation roughly 3 years before you encounter Dirac's equation, but that's not the answer you're looking for. Schrödinger's equation gives you a quantum mechanical description. However, Dirac's equation does something more. It does the same for electrons. There's this concept of spin. I will not go through the concept, but I'll point you one simple thing. Some particles like each other. Other particles do not. Some particles you can compress, and these particles would not be angry at. Well, whereas electrons, they have spin half. They are what we call as fermions. These fermions, you put them too close to each other, they feel this thing called Pauli exclusion principle, which you will soon read about. What Dirac did is Dirac asked, okay, they have this spin, they feel this weird way. Can I write down the equation for that? And this equation too must suffice the energy momentum principle. That what do we know? We know equal to mc square, but it can be written in a different manner. E square, energy squared, equals to momentum squared plus mass squared. Dirac equation satisfies that as well as the properties of electrons. Schrödinger's equation, on the other hand, is the non-relativistic version of it, and for objects without any spin. It simply says that, look, your total energy equals to kinetic energy plus potential energy. So yeah, this is the difference.
Maybe I think you should also tell people that spin should not be considered as
Yes. Yes. There's nothing spinning. They just behave like they were spinning in a different manner, like when they couple to magnetic field. But actually, like when you think of spin, what do you think? No, the particles are not actually spinning. It's a fundamental intrinsic property of the particle that scientists decided to name as spin. In retrospect, maybe we should have come up with a anyway. Yeah. Okay. Any other questions? Just 1 second. So just let us go through over the online questions and.
Anya Shah asks, can one light particle or photon bounce off another bit of light? Can photons scatter from each
other? So Anya Shah asks, can one light particle photon scatter off of another photon? Can photons scatter off of each other? I'm not sure about the answer to this question. I know that in principle they can, but have it been observed? Arnab?
I don't know, I'm thinking about it.
Right. No, even if you send a single photon at one time, right? Maybe you send one photon per second. Okay, so okay, just for the online audience, the question was, does the double slit experiment explain that? The answer is no, because even if a single photon is sent maybe per second and then you send it for a day, they go through these both slits and they interfere. This is not the same thing as scattering with another particle. Okay. Any? Yes. So yeah. So no, not in double slit. Yeah, but in principle, theoretically, I know the Feynman diagrams allow the photons to scatter, but I do not know whether it has been experimentally observed. Okay. Great question, by the way. Please, yeah, ask those questions more. I'll just send it to Arnab's way.
Okay, let me see if there's any other here. So there's this question from Abhinav Chaudhary. Is Planck length the fundamental limit to the space-time?
Abhinav Chaudhary asks if Planck length is a fundamental limit to space-time.
And is it possible to breach?
Is it possible to breach it? The correct answer would be we do not know, because neither have we. See, some people will say yes, but my take on this is this: science is what you observe. Unless you actually go to Planck's length, try to breach it, and all hell breaks loose, you cannot say for certain what is the fundamental limit to nature. Maybe it's broader, maybe it's even lower. We don't know. But yeah, so that's the answer I would give.
Another question.
And please correct me if you disagree. So I would strongly suggest that you talk to a string theorist about this. I am a humble particle physicist working on neutrinos. I do not know the answer to this question. And you may, of course, think that I might email you back the answer. But no, I do not know the answer to this question.
Okay, I don't know anything on quantum mechanics. I am an experimentalist. I observe, and I can observe that the chai is getting cold.
Right.
So we must say thanks to you. Before we wrap up the online part, you guys don't worry. There's lots of time for questions after we have chai and come back. But we will stop the online thing. So let me announce the next 2 chai and chai sessions. 15 days from now, the mid-July session at Ruparel College is going to be on how to build better proteins.
different types, something called circular permutations of proteins. That's happening in the middle of July. And a month from now over here, the first Sunday of August, we are going to go to the world of maths. Radhika Gupta is going to tell us something about, can't remember, but it's maths. The next one here is maths. The one in Ruparel 15 days from now is chemistry. On that note, online audience, sorry, you don't get chai. You can still put in your questions in the chat and I will put them Divya's way. Meanwhile, audience here, let's go outside, have a cup of chai, start some discussion, then come back. And I'm sure you have lots of questions for him, whether you understand and not understand both. So on that note, let's thank Divya for taking us to this interesting.